So let's get into analyzing acceleration and other things from a velocity time graph. So a little different than the previous graphs. This is not measuring displacement. It's measuring the velocity of the object with respect to time. Velocity, of course, you have positive velocity, you're moving in a positive direction. You have negative velocity, you're moving backwards or in the negative direction. Again, you can have the first and the fourth quadrant because of that. We are, again, not going to move backwards in time. And you'll note the first segment here. At time equals 0, again, we don't always have to start at the origin, but at time equals 0, for whatever reason, we were looking at the object and it crossed the starting line at a velocity of positive 5 meters a second. And it continued to travel at 5 meters a second for that first second. And the object is moving. Unlike distance time graphs, when a flat line was no motion, here on a velocity time graph, a flat line is constant velocity. It's moving at 5 meters a second for that first second. That's what the graph tells you. And we contrast that by looking at what happens from the first to the second, where the velocity is changing. We are speeding up now. And we're speeding up at a pretty decent pace here. We go from a speed or velocity of 5 meters a second, we jump to a velocity of 20 meters a second, and we do that in 1 second. And we can now, because of that, find the acceleration during that 1 to 2 second time span. Because if we read the graph and get the points, we know average acceleration is change in velocity over change in time. So we change from 5 to 20. So we end up at 20 meters a second. We started at 5 meters a second, and we did that in 1 second. I'm not really doing sig figs here too well, am I? And we end up with a change, an acceleration, average acceleration of positive 15 meters per second. Now, I guess for posterity's sake, let me do this. You get the idea, and I do apologize, but it's just going to make the sig fig work a little easier. And this should be, of course, two sig figs, fine. That works. Now, that's an appreciable acceleration. Oh, meters per second squared. Have to fix that too. Now, realize that this change in velocity over time, again, is a slope. Rise, change in velocity, run, change in time. And so slope pops up again, but in the distance time graphs, slope found you velocity. In the velocity time graphs, slope finds you acceleration. So be careful of when you're using slopes of lines on which graph you're on and what that means. Because it's going to get tricky as we move forward into the year. If I look at that same kind of analysis from 2 seconds to 5 seconds, so I have this long straight line, so the object obviously starts slowing down, continues, slows down. Wait a minute. Well, you know what? Hold that thought. There's a couple things that should raising some red flags in your head, but we'll get to that. Let's just find the acceleration during this segment. The acceleration is easy to find because all you have to do is final minus initial velocities over the time, which again is the slope. So we can do the rise over the run, or the acceleration formula. It's the same. That's supposed to happen at 2, by the way. So again, hand-drawn graph, sorry. So we go a change in velocity, which goes final, which is a -10, minus an initial, which started at 20. So that's a change in 30 meters a second. And we're going to do this over 1, 2, 3 seconds. And again, I'm losing my sig figs here. Sorry about that. Let me clean this up. I guess I could show the actual subtraction here. I did that in the previous example, so I can go. And if you do this, you're going to get basically -30 over 3, which will be -10.0 meters per second squared. It's negative because, well, it's a downward slope, definitely. Negative slope, there's no doubt about that. Math class told me it's a negative slope, but we have a problem. -10 acceleration typically means -10, you're slowing down, which would be true. But then also, one of the previous lessons we learned, a -10 could be speeding up in the other direction. So what's going on? You gotta be careful. You have to think about given information and what the graph is telling you. Well, let's look at it. We started at 20 meters a second, and we started slowing down. We know we're slowing down because we go from 20 meters a second to 15 meters a second to 10 meters a second to 5 meters a second, and then we reach this critical point. And what happens there? Well, at this critical point, your velocity is nothing. You don't have a velocity. You've stopped. But then we keep going. But in the negative direction. And we go from 0 to -5 to -10. We're getting faster now. Because -5, and remember, -5 means you're going 5 meters a second in the opposite direction. 10 meters a second in the opposite direction. This is very, very, very significant. You were moving fast forward. You started slowing down, 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 slowing down. You stopped for a moment. You didn't stop for very long. And then suddenly you threw it in reverse, turned around, and started running back in the other direction. That's what this tells you. And all the while, the acceleration remains absolutely constant. It's the same acceleration throughout the motion. And you're like, how can that be? How can the motion have the same acceleration but in two separate directions? Well, hold on. Tennis ball. And if I throw it into the air, while it's in the air, it goes up, pauses a second, and then falls back down while it's in the air. Not when it's in contact with my hand, only when it's in the air. Well, what causes that to happen? Gravity. Gravity's acting on the ball. Does gravity act differently on the ball as it's moving up versus it's moving up versus moving down? No. Gravity acts the same all the time. Gravity is always trying to pull the ball down. If the ball's moving up, gravity's trying to pull it down. If the ball's moving down, gravity's still trying to pull it down even more. And so all the while, in motion, the gravity pulling down, causing that acceleration to remain the same. As it moves upward, it loses 10 meters a second of speed every second. And then when it stops for a moment, it turns around and it's going to gain 10 meters a second every second downward. Because as it moves up and it's losing speed, it's really still just trying to be pulled down. Let that sink in. It's a tough thing to handle when you first learn it. It's a little like, whoa. Okay? We're going to talk more about this, but yeah, that's a constant acceleration. And you were slowing down, stop for a moment. Once you cross that time axis, you stop. And then you turn around, go in the other direction. Okay. I know, wild, right? Once we reach this point, and we go to here, suddenly we can't do a slope anymore. These are nice constant accelerations. They're the same acceleration throughout the entire little segment of motion. Here we have a non-constant acceleration, which we won't deal with much in this class. Can I do an average acceleration from this point to this point? Yes, I can do an average acceleration, but I can't say it's constant. You could do final minus initial. So we end up stopping. The initial speed or initial velocity was -10. And we did this from 7.0 to 5.0. So we ended up being a positive, because negative is positive, 5.0 meters per second squared. That's reasonable. The last piece of the last segment of the graph, obviously you are not moving. You have no velocity, you don't change velocity, so you are not moving, zero velocities and zero acceleration, so nothing is happening there. All right, so there's one more piece I do want to teach about velocity time graphs. One more quick little break. Let me clean up the graph and then we'll have that discussion.